All right, so today we will start again. I'll make a minor recap of what we did yesterday in the other lesson, and then we continue with today's lesson. But as I said, this session is purely considering the second order linear equations. And then we define the second order linear equation as y prime plus a1 of c y prime plus a naught of c of y to be equal to b of c. Okay. Then
Yes.
we said few things about this. One was that if b of c is equal to 0, then we say it is homogeneous. 2, if a1 and a0 are constants, then we say that the second order has constant coefficients. Okay. If both a1 and a2, a1 and a0 are constants, then we say that this linear equation has a constant coefficient. The third one, if a1 or a0 is not constant, okay, then we say that the equation has variable coefficients. Okay, so this is what we said, and then we try to solve some equations based on this idea of the definition of the second order linear equation. And of course, what we then did was that we defined an initial value problem of the second order. And then we said that if you have second order or initial value problem, then you have a1 of c of y prime, a naught of c of y is equal to b of c. Then, as we know from initial value problems, you need boundary conditions. Okay, so boundary conditions means that you need c0, okay, which is equal to y0, and then because the second order, you will need a first order derivative of the derivative of the y term as well to be a boundary condition. So this is how we define then an initial value problem where we said a naught, a1, and b are continuous in a closed interval I, which is actually a subset of R. Okay. So continuous in an interval I, which is a subset of I. And then this initial is a constant in I. And then we have Y. The initial conditions as well are also arbitrary constants. So this is how we also defined an initial value problem of a second order. Okay, of course, it also means that we can say that it is homogeneous, or it has constant coefficients, or it has variable coefficients based on how this equation is posed. Okay, based on how this equation is posed, you can say this is the second order of constant coefficient or variable coefficient. All right. Then we spoke about some properties of also the properties of homogeneous equations. Okay, we spoke about the properties of homogeneous equations, and then this we said that you can write it as a, you can write, so some properties, talk about some properties. And what we said was that if you have a function L which represents, so if you have a function Ly, which is representing your second order equation, okay, then you can write where we have is equal to f of t, then you can write this, then finally as Ly is equal to f. Okay. Okay. Then you can write this as Ly is equal to f. And this is really critical because then you say that this is a linear operator. Linear operator. And then we said something about the linear operator. We said that if you have a linear operator, then you can satisfy if you have C1y1 plus C2y2, then the linear operator should give you LC1 of y1 plus C2L of y2. You should be able to do this for a linear operator. Okay. Then what we said again was that you can do superposition. Superposition. We spoke about superposition. So for superposition, what we said is that if you have a linear operator and you have its solutions to some homogeneous, and you have some solutions y1, y2 to some homogeneous equation, then every constant holds. So for superposition, we said if you have L1 to be 0 and you have Ly2 also to be 0, for every, okay, for every C1, C2, it holds that you can say LC1y1 plus C2y2 is equal to 0. Okay, is equal to 0. And then the result is not true for non-homogeneous equations. True. Then we spoke about linear dependence. Linear dependence. So for linear dependency, we said, let me say definition here. For linear dependency, we said that if you have two functions, y1 and y2, we said they are linearly dependent. Okay, we said they are linearly dependent if and only if they are proportional. Okay, they are proportional. And then we made some remarks. That one, if you have y1 to be of t, then you have to cy2 of t, where c is a constant. Okay, then this is proportional, constant, and this is proportional. Then 2 is that y1 is equal to 0, is proportional to every other function. Okay, it's proportional to every other function. It means that you can say y1 is equal to 0 times y2, and it's the same, it's proportional to every other function. Anyway, so if it is not linearly dependent, okay, then we say that it is linearly independent. So if it is not linearly dependent, then of course the only thing we can say is that then it is really linearly dependent. Okay. Then we went on to talk about the Wronskian. Okay. Okay, the Wronskian. So we introduced the Wronskian function and then we verify some properties, okay? And then also for this reason, we went on to talk about some Abell's theorem. So what was the Wronskian? We said the Wronskian of the differentiable functions, okay? So if you have y1 and y2, which are differentiable functions, then W12 of t is equal to y1 of t is equal to y1 of t, y2 prime of t minus y1 prime of t, y2 of t. Okay, and then we said this was the Wronskian. And then you can see that immediately you realize that it is really nothing else but the determinant of a certain y1, y2, y1 prime, y2. All right, so that is actually what the Wronskian is about. All right, so you can set examples. We did some examples, and then we said that if the Wronskian, so we said some things about the Wronskian. We said one, if the Wronskian at the initial value is not 0, okay, for t not in I, then y1 and y2 are linearly independent. Okay. So if the Wronskian of some points t naught is not 0, then it means that y1 and y2 terms are linearly independent. Then next is that we were able to show that the Wronskian of two solutions of a differential equation satisfies a differential equation of its own. Okay, and this was what gave us what we call the Abell theorem. Okay. We said that if you have y1 and y2, which are twice continuously differentiable, okay, which are twice continuously differentiable, then of y prime prime plus a1 of t y prime plus a naught of t y is equal to 0 for a naught a1 continues in an interval I. Okay. Then the Wronskian w12 prime plus a1 of t of the Wronskian is 0. Okay, and then when from this we know that from this we can solve for W12, right? So we solve for W12 from here, and then we'll have W12 of T0 exponent minus A1 of T, where A1 of T is nothing else but the integral from T0 to T of A1 of S Okay. So this is what we also said about Abell's using Abell's theorem. But if you have two solutions which are two functions which are twice differentiable continuous, and of the second order homogeneous linear equation, then the Wronskian solution should also give us something like this. Okay, and then this we're able to prove it as well, and then work out some one or two one example. So today we are going to talk about reduction of reduction. So today we are going to talk about methods. Okay, reduction of the order methods. Reduction of order methods. Okay, so what happens is that sometimes you have a second order linear, you have this second order linear equation, but you will be able to reduce the order from second order to first order, for instance. And that is the whole idea about this and how to do it. But before that, we will talk about some special second order equations, and then we'll talk about how to solve them as well. So if we have a second order differential equation, we call it, it's a special, so we call it a special second order equations, okay? So we call them special when neither function or its first derivatives or independent variables does not appear explicitly in the equation, okay? So when you do not have either the function or its first derivatives or the independent variable that does not appear in the equation, then we say that it's a second order special or special second order equation. Then in these cases, you're able to transform it into a first order equation for a new function. Okay, so what it means is that, so if I have to define, then you say that a second order, okay, second order equation in the unknown y, okay, in the unknown y is y prime is equal to f c y prime. So this is the second order in the unknown y. Okay. Okay, here, so what happens is that our function f, our function f moves from R3 to R.
Uncle, have you called me? Okay.
Then so the second order differential equation here, we say that this is special, okay. This is a special second order, differential equation if and only if A, we have y prime prime, B, y prime prime, C, y prime prime. Okay. So first then is if the function y does not appear in, so we have C and then y and y prime. You say if the function y does not appear okay, does not appear explicitly in the equation, then second order equation is a special one. Or the second one is that if the variable t also does not appear, so second one, if the variable t also does not appear in the equation, so, and then the third one is the variable t, and then the derivative of the function also do not appear. So in this case, we have f t of y prime. In this case, we have f y prime. And then in this case, we have f of y. Okay, so if we have an equation that looks like that, then we say that this is of a second order. Okay, it's of a second order. All right, so usually what we know is that whenever we have this kind of special second order, then it's usually easier to solve. Okay, so let's take them one by one. Let's take the first one, A. Let's take the first one, A. A, okay, A, where the function y is missing. So here what we say is that for A, have a theorem that if the second order differential equation, okay, if a second order differential equation has the form y prime is equal to f c y prime, then v is equal to y prime satisfies the first order equation such that v prime is equal to f c of v. Okay, so all we're saying is that you can make a substitution of this term here to be v, and then now solve your v prime to be f. Okay, that will give you your second order or into lower order. Okay, so example is that we can have y prime is equal to 2t y prime squared with initial condition y0 is equal to 2 y prime of 0 is equal to -1. Okay, so step 1, we said introduce v such that this v is equal to y prime. Then it means v prime will be equal to nothing but y prime. Okay, so if you take v to be y prime and then v prime to be y prime, then immediately you see that you have v prime is equal to nothing else but minus 2t v squared. Okay, because this here is already v that we are substituting. Okay, and then once you have that, of course, then it's possible to write v prime over v squared is equal to minus t. And then this is nothing but minus 1 over v is equal to minus t squared plus c. So, of course, this is nothing but just integration. Okay, so now we know that 1 over v is equal to minus t squared plus c. And now we know v is the derivative. So now we just make a substitution so that we have now minus 1 over v. V we know as y prime is equal to minus t squared plus c. Okay, so y prime will be nothing but 1 over c squared minus c. Now that you have this one, with the initial condition given, so you say that minus 1 is equal to y prime of 0. So it means that if I put c to be 0, I'll get 1 over minus c. Okay, and that means that c is nothing but minus 1. Sorry, it's nothing but 1. Okay, so c is nothing but 1. And then if c is 1, then it implies that y prime is also 1 over c squared minus 1. Okay, so now our aim is then that now that we have y prime is equal to 1 over t squared minus 1, we can easily solve this by integration. Okay, so to solve for this is basically nothing else. This is y prime is equal to dy is equal to 1 over c squared minus 1. So you take the t to the other side, then you have dy is equal to dt over t squared minus 1. Okay, then you find the integral. You find the integral, so you apply partial fractions to the other side. And once you do that, you'll be able to resolve your equation successfully, and you will get something like that. So you will get, you'll be able to derive finally that y is equal to half into brackets ln t minus 1 minus ln t minus 1 or plus 2. Okay. Sorry, it should be plus 2, minus and plus, or plus 2. Okay. Then the next one is for case B. Case B is when t was missing. Okay, so when we have y prime prime is equal to f of y and y prime. Okay, so for that one, if we have an initial value problem like that, then y prime of 0 is equal to y1. If you have an initial value problem like this, then we say that there's an invertible solution y, then the solution w of y is equal to v of t of y. Okay, where we have an invertible solution y. So, of course, similarly, here as well, we know that v of t will be nothing but y prime. Okay, and cy will be the inverse of yt to satisfy the initial value problem. And c of y is the inverse of y of t and satisfies the initial value problem. W is equal to f y w all over w. And wy0 is y1. So the proof is really not that complicated. It's just like chain rule. Okay. So this is the second one when the time is not there. So in that case, we have only a special dependency. Okay. Then the next thing is that we do is that we take an example, which is find a solution y to the second order equation y prime prime is equal to 2y prime. Okay, so now since the variable w does not appear in the equation, we start. So now solution 1, you introduce bt to be equal to y prime of c. Then we know we know y prime. Okay, we can easily write it out, right? Because of course, if we have vt is equal to y prime of t, then it implies v prime of t is nothing but y prime prime of t. So immediately we can write this out. Okay, then we can write it out as v prime of t is nothing but 2y of t, and then I don't use y prime again, but I use now v of t. Okay. Okay. So this is just after making your substitutions. Then it means that this function satisfies, or we look for an invertible solution first. Invertible solution. So invertible solution y. So we introduce w of y is equal to v of t of y such that the function satisfies, we have w prime of y is equal to dw over dy, which is equal to dv of dt of dy c of y, okay, which is equal to v prime of y prime of t of y is equal to v prime of v of t of y. Then using the differential equation, we can write it as that is 2y of v all over v c of v. t of y squared. And this is nothing but the w dy is equal to 2y, and this gives us w of y is equal to y squared plus c. But since we say that v of t was equal to w of y of t, then v, so this is w, then v of t will be equal to y squared of t plus c. Okay. Plus c. So, but we know that y prime is equal to v of t. It's a separable equation. So we can write y prime over y2 plus c is equal to 1. Okay. So now the next step is to solve for y prime, to solve for y when we have such an equation. Okay. So of course, here we can decide to leave the c constant to be there, then just play around with it. But we just want to see the behavior, how this whole function behaves. And since it's a constant, we can rewrite this as dy of y squared plus 1. Let's consider y squared plus 1 is equal to dt in this form. And then when it does that, of course, what we need to do is to find the integral. And then when we apply the integral, we will have nothing but a tan inverse of y to be equal to t plus c0. And that is nothing else but y of t is equal to tan of t plus c0. Okay, so that's a simple example, but just to show you how the whole thing works. So you have your second order equation. You make a substitution for one of the terms, which is vt is equal to y prime of t. Then what you do next is that if you know that the second derivative is equal to the substituted term that you are using, okay, and then so you have the substituted term you are using that you can now replace with v inside the terms. So now you take invertible solution such that you can rewrite this invertible solution in terms of v prime and v that you have used. And once you have it, then you go ahead and solve for your y in a systematic way. Okay, so hopefully that you understand now how to apply these things now. Okay. Okay, so the fact we are now able to realize, so let's go systematically Now, if you write a theorem for the reduction of the order, reduction of order, then we say that if you have a non-zero function y1, which is non-zero, and it's a solution, okay, it's a solution to y prime prime plus a1 of t and y prime plus a naught of t of y is equal to 0. Of course, here we say a naught and a1 are functions that are given. And the second order solution is not proportional. Then, okay, the solution is not proportional to y1. Okay, and y2, which is given by y1 of t integral e minus a1 of t all over y1 squared of t dt, where a1 of t is equal to a1 of t dt. Okay, all right. So now, in the first part of the proof, what we did was remark is that we wrote y2 of t to be equal to v of t of y1 of t. Okay, this we did in the first part of the proof. Okay, if and only if the function v, so we did y2 of t is equal to v of t, and then y1 of t, y1 of t, and then we said that we can write v prime prime plus 2y1 prime of t over y1 of t plus a1 of t v prime is equal to 0. Okay, so in the second part, we solve the equation for v. So here, then we solve for v, of course. Then this is the first order equation. So if you solve for v, then what you can do is that you can now write w is equal to v prime. And then since v itself does not appear in the equation, we also determine this as really the second order. Okay, so next is that the equation for w, okay, is linear and first order usually in this sense. And then the other one is that once you have an equation which is linear and first order, we can solve using the integrating factors. So one is that so W equation is linear and first order, okay, and first order, and that means that, and that implies you can use integrating factors. Integrating factors. Integrating factors method to solve the equation in that sense. Okay. All right. So let's take an example here. Find second solution y2, which is linearly independent to the solution y1 of t is equal to t of the differential equation t squared y prime prime plus 2ty prime minus 2y is equal to 0. So let me write this as solution. So solution here is that 1 y2 of t is equal to tv of t. Okay, that's y1 given. And then this implies that if we do y2 prime, then we have t v prime plus v by product rule. And then if we do y2 prime prime, then we will have tv prime prime plus 2v prime. Okay, so if we do that, then we have 0, which you now can say is equal to, so we just make a substitution. Okay, make a substitution here. So we have t squared, and then we have y prime prime. So this is tv prime prime plus 2v prime plus 2t y prime, which is tv prime plus v minus 2y, which is tv. Then we expand, so in the end we have something like 3v prime prime plus 4t squared v prime. And this is nothing but v prime prime plus 4 over t v prime is equal to 0. Now, since the second equation looks like something we know already, we can make some substitutions. So now from here, we can make y1 to represent t, and then p of t to be 2 over t. And this will already mean that we have t v prime prime plus 2 plus 2 over t prime of v prime is equal to 0. So now we have the equation in terms of v, which is in terms of v. So we now the equation for v, we go to the first order for the equation of v by making a substitution for w. So we say w and then w prime, okay. So which is given by w prime over w is equal to minus 4 over t, and this can easily be solved. So in the end, you have wt c1 t to the power minus 4, where c1 is a real constant value. So if you know w, then you can easily write out a solution for v, because we know w is equal to v prime. So now we can write v, okay, v is equal to c2t minus 3 plus c3, where c2 and c3 are in the reals. Then finally, we know that y2 is equal to tv. And now that we know v, we can just make a substitution for y2 such that it is equal to c2. So it's c2 minus t to the power minus 3 plus c3. And this is nothing but c2t minus 2 plus c3 of t. Okay. So if you have that, then it means that we can write our y2 to be c2 of t minus 2 plus c3 of t. Okay. Then if you choose, so choose c2 to be 1, c3 to be 0, and we'll have y2 is equal to y2 of t is equal to t minus 2. So therefore, we have y1 of t, which is equal to t, and y2 of t is equal to 1 over t squared. So we have reduced this into first order. Then, what about if you have homogeneous constant coefficients? Okay, homogeneous constant coefficients. What if we have homogeneous constant coefficients? So when we have a homogeneous constant coefficient, so the solution to the second order linear homogeneous equation can be obtained by non-proportional solutions. Okay, this we have already discussed. Then we said that we can obtain two linearly independent solutions in a particular case that the equation has constant coefficients. In that case, the problem we say that reduces to solve for the roots of the degree 2 polynomial or the characteristic polynomial. So we say if two linearly independent solutions have constant coefficients, we are able to reduce to solve the roots of a degree 2 polynomial, or called a characteristic polynomial. What is this characteristic polynomial? So roots of characteristic polynomial. So we have already said that we only needed to find two linearly independent solutions to second order linear homogeneous equations. Okay, so if we have a solution which is a linear combination of the two, then how do we find a pair? So here, to find the characteristic using the characteristic equation method, so example is this. If you have y prime prime plus 5y prime plus 6y is equal to 0. Solution. How do you go about this root of characteristic polynomial? Okay, so first is take a test function. Okay, take a test function, and then take a test function having the derivatives, okay, proportional to the original function. So example is take y prime is equal to r y of t. Such function will be simplified from the equation. So if you have y prime of t is equal to r of t, then it implies y of t is nothing but e to the power r. So we can introduce such a y. Okay, if we introduce such a y, then it means that you take y, which is equal to e to the power yt. You take y prime, which is r to the power to e to the power rt. So we have y is equal to e to the power rt. Y prime is equal to r e to the power rt. Y prime prime is equal to r squared e to the power rt. And then now we substitute it into our equation. In that case, we will have r squared e to the power rt plus 5 r e to the power rt plus 6 e to the power rt is equal to 0. Then in that case, we have r squared plus 5r plus 6 e to the power rt is equal to 0. And this is nothing but r squared plus 5 plus 6 is equal to 0. And when we solve for this, we see that r is equal to -2 or r is equal to -3. Am I correct? No, plus 2 plus 3.
So it's 5R.
Sorry, 5r.
Hello?
Yeah, you are correct. 5r. So 5r, then we have plus 2 and then plus 3. Okay, for r. So if we have that, then wait, so we have here, plus 2 plus 3. So R will be equal to minus 2 and minus 3. Okay. And then it means that we have y1 of t is equal to e minus 2t, and y2 of t is equal to e minus 3t. And finally, we have y of t, which is equal to c1 e minus 2t plus c2 e minus 3t for c1, c2 in R. So from the example above, you will see how we have used this idea of the characteristic polynomial. So definition is that the characteristic polynomial, okay, the characteristic polynomial and characteristic equation, okay, and a characteristic equation of y prime prime plus a1y plus a naught y prime is equal to 0, where a1, a naught are constants, are given by P of R is equal to R squared plus A1R plus A naught, and P of R is equal to 0 is given. Okay. So if you are given any second order equation, linear homogeneous equation, you can immediately write out the characteristic polynomial as well. And then once you have this R squared, then immediately you can write out your solution, which is half minus A1 plus square root A1 squared minus 4A naught. Okay. Then once it's a quadratic equation, you know the solution of the quadratic equation. So a few things just you have to think about, and that is with respect to the discriminant. Okay, this guy here, we call it discriminant D. So first, few things you have to think about is one, what is the nature of D? Is D is equal to 0? Is D greater than 0? Or is D less than 0? 1, 2, 3. Okay, we say that if it is positive, then we have, if it's positive, like this guy, then we have different real roots, right? Different real roots. If it is less than 0, that is negative, then we have complex conjugates pair, and then here if it is 0, then we have repeated right? Real roots. So these are the three things that we will get if based on the determinant or the discriminant, okay, discriminant. Based on the discriminant in the of the root, the discriminant. Okay, so we have a theorem that's for the constant. We have a theorem that states that if you have the roots of your characteristic polynomial, if R plus are the roots of the second of the characteristic polynomial to the second order linear homogeneous equation. So if R plus, sorry, are the roots, okay, are the roots of y prime prime plus a1y plus prime plus a prime. And if c plus c minus are arbitrary constants, then A, if R plus is not equal to R minus, then the general solution is given by yg of c plus e r plus c plus c minus e r minus c. 2. If r plus is equal to r minus, then we give it 1, which is r0, and they are all in r. Then the general solution, then yg of t is equal to c plus e r naught of t plus c minus of t e r minus r naught, sorry, of t. So if the roots are repeating, so this is the case for repeated roots, okay? This is repeated roots. Repeated roots. This case here, okay? Then you need to be sure that there's a t coming here. All right, but apart from that, if we are in the different real roots, then you have this one as well. So that's the main difference between these two. If you have a repeated roots, and then if you have independent roots. Okay. So we can consider an example. We can consider an example like y prime prime that we already did consider. Y prime plus 6 is equal to 0. Y of 0 is 1. Y prime of 0 is minus 1. For here, we know that the general solution was something like c plus e minus 2t plus c minus e minus 3t. Okay, so we know that at t is equal to 0, we have 1. So 1 is equal to y of 0. And then at t is equal to 0, we just have here c plus c minus. Then we know that at y negative y prime, okay, so y prime at t is equal to 0, we have minus 1, okay. Minus 1. And then y prime is nothing but this guy here. And if you do it, you get minus 2c plus e minus 2t. Then you get minus 3c minus e minus 3t. So if you put t is equal to 0, then you have minus 2ct here, then minus 3c minus here. And then you can solve this simultaneous equation and get c plus is equal to 2, then c minus is equal to minus 1. Y of t is equal to 2e minus 2t minus e to the power minus 8t.
Hello,
Hello.
please. Instead of using C plus C minus, can you also use C1, C2?
Yeah, so I feel that's actually a bit of a better notation.
No
C1,
problem.
C2, so that this plus minus looks too tricky.
Yes.
So yeah, correct. Maybe I'll just change the notation and then use C1, C2, C1, C2, C1, C2, C1, C2, C1, C2, in that manner. So you are right. That's a better notation, I would say. Okay. So, of course, we can do another example, but that you have to try it yourself. And there's another example. There are other examples that are in the book. So you should try it, working it out, and see. It's very straightforward, and then you can play with it. The only part is when we have, the only critical part is when we have complex roots. So real roots for complex, not real solutions, sorry, real solutions for complex roots. Okay, that's the most important part. So we know that we actually said that if the discriminant is less than 0, then we have complex conjugate parts, okay, pair. So basically it means if a1 squared minus 4a naught minus 4a naught is less than 0, then we have R to be alpha plus or minus I beta. So maybe I should say R1 2 instead of plus and minus again, right? So maybe I should say R1, 2 will give us alpha plus beta, where alpha is equal to minus a1 over 2, and then beta is equal to square root a naught minus a1 squared over 4. In that case, the fundamental solution, if you have such a situation, then the fundamental solution y will be equal to E alpha plus or minus beta all into bracket T. Okay, so I'll say Y12 as well. Okay, so we'll have a system where we have Y prime of 1 is equal to E alpha plus I beta of T, then Y2 of prime is E into bracket alpha minus I beta of T. Of course, when we do that, then it means that the general solution will then be written as C1, okay, Y tilde 1 plus C2, Y tilde 2, where C1 and C2 are all complex numbers, so in the complex field. But usually best is that they are real. I think that should be enough. And this gives us a general solution for when we have complex valued systems. So we have a proof, we have a theorem, for real value fundamental solutions that if the differential equation dE, let me not say dE because I know what it is. If y prime prime plus a1 y prime plus a0 y is equal to 0, and a1, a0 are real constants, are real constants, okay? They are real constants. Then we have a complex root, I'll say 1, 2 to the alpha plus minus I beta. And complex valued fundamental solution. Okay, complex valued fundamental solution y tilde 1, which is E alpha plus I beta of T, and then y tilde 2, which is E alpha minus I beta of T. Then y1 of T is equal to E alpha T cos beta T, and y2 of T is equal to E alpha T of sine beta T. So in essence, your y tilde, which is E alpha plus I beta, this I beta part, you can write it as cos, and then because of the plus, and then if it is minus, you can write it as a sine part. And then the proof for that is very, very straightforward as well. Okay. So maybe we take an example. So if we take an example, then we say that we can say y prime prime minus 2y prime plus 6y is equal to 0. Find a real general solution. So solution is that if you have this, then you know you can write it as minus r squared minus 2r plus 6 is equal to 0. And then if you solve that, then you know that r is equal to 1 plus or minus I square root of 5. And that means that you have R1 to be plus I square root of 5, and then R2, 1 minus I square root of 5. And when you do that, then it means you can write y tilde 1 to be E1 plus I square root of 5, and then y tilde 2 to be E1 minus I square root of 5. And then when you do that, you have y1, you can have it as E of t, sorry, there's t attached. E of t cos square root of 5t, and then y2 is E of t sine square root of 5t. And then the general solution, you can write as C1 cos square root of 5t plus C2 sine square root of 5 of t all into bracket times E of t, where C1, C2 are all real. Okay, so in that case, you have your solution on the gate. So in the lecture notes, you see that there are more examples that you just have to play with and then try your hands on as well. All right.